proof of, last time we looked at the proof of the chain rule. And in the tutorials in the last couple of weeks, we've been looking at other techniques of differentiation, logarithmic differentiation, implicit differentiation, and so on. And for the next couple of lectures, and to finish off this chapter, we're going to look at some applications of the derivative. And there's four kind of applications here. Or well, there's a few application areas listed here to do with finding and classifying stationary points of functions. And that's related to solving various kinds of optimization problems. We'll also do a little bit on the idea of curve sketching, being able to pick out the important features of the graph or the curve of a mathematical function. We'll also do a little bit of material on kinematics, which is some simple modeling of the motion of objects in the presence of forces or accelerations. Okay, so we're going to look at these kind of things and see the derivative being used in various ways. So today we're going to look at we're going to have another little look at Taylor series, okay, which we looked at already last term when we were looking at series in general. And then in the second half of this morning's one, we're going to look at the material on finding and classifying stationary points of functions and some basic optimization type problems. Okay, so we met the definition of a Taylor series back in term one, and it clearly is an application of the derivative, because the derivative features in it. So just to remind you what it was, the Taylor series is an example of a power series. A situation where you have a function defined by an infinite polynomial in the argument to the function x. So here's a situation where you've got f of a plus x, so a is some fixed point. A is some fixed point, so we speak of this Taylor series being a Taylor series for f about the point A. So A is like a base point, and then x is a little variation off of A. Okay? And so this Taylor series tells you what the value of the function at the point A plus x. Now x could be positive or negative, so you can move either side of A. And it's an infinite polynomial in x. So you see here it's a sum over the index n from 0 to infinity of something times x to the power n. So it's an infinite polynomial in the variable x. And the coefficients of that polynomial, this f superscript bracket n, well, that stands for the nth derivative of the function f. The 0th derivative of the function by convention means just the function f itself, undifferentiated. So f1 then be the first derivative, f2 be the second derivative, and so on. So the coefficients of the Taylor series are the various derivatives of f evaluated at the base point A and scaled by the value factorial of n. The formula kind of simplifies somewhat when you have the base point A as being A equals 0. Then the left-hand side becomes simply f of x. If using the base point A being 0, then the left-hand side will just be f of x. And the right-hand side then is, well, the same as before, except this time we're talking about the derivatives being evaluated at the point 0. Now, in the table below that, so this is on page 48, there's some Taylor series or Maclaurin series of some standard functions, and you can find a lot of these in the formula handbook as well that we have in exams. And they're a useful tool to have for functions in various situations when you want to integrate or differentiate functions and get approximate values, and combine functions in different ways, because it gives a kind of standardized view of a function. If you can view all functions that you're dealing with in terms of polynomials, or approximate them well by polynomials, then that gives a kind of standardized way to treat functions. So the idea with these power series is that, okay, you might get exact equality when you take the whole infinite series. And of course, they do have an associated radius of convergence that we discussed last term as well. So they might only be valid in a certain range of values of x. So you might get exact equality when you take the whole infinite series, but if you just take a finite part of the series, well, you don't get equality, but you will get an approximation to the value of the function. And the more and more terms of the series you bring in, the better and better that approximation becomes. Okay. Now, what we might show you now on the overhead is just a little argument which goes some of the way to justifying the existence of these things, and why that formula for the Taylor series, why that formula is correct. Okay. So first of all, recall if we recall the alternative definition of the derivative that we gave the other day. So this is where we consider the value of the functions f at a base point A and a small variation x off of that. Okay, I called it h last time, but to fit in with the notation of the Taylor series, I'll call it x today. But we saw that that was the value of f at A itself was x times the derivative of f at A, and then it was x times an error function of psilon x, where psilon x converged to 0 as x converged to 0. That was the alternative form of the definition of the derivative that we introduced last time. The derivative of the function f is the correct number which goes into this formula, gives you this equation for values of the function f nearby to the point A. So this part here was the linear approximation. Linear approximation. And this was the error term associated to that linear approximation. And comparing this to the Taylor series formula, we see that they agree. They agree on what the linear approximation is. Okay, because if you take the formula for the Taylor series, f of A plus x is summation n equals 0 to infinity. The nth derivative of f evaluated at the point A over n factorial times x to the power n. Well, if you look at the first few terms of this, what do the first couple of terms of this look like? Well, when n is 0, we've got the 0th derivative of f. The 0th derivative of f is just the function f itself. Function f differentiated 0 times. That's just the function f evaluated at A, divided by 0 factorial, which is conventionally 1, times x to the power 0. That's the first term. When n is equal to 1, you got the second term, so that's the derivative of f evaluated at A, divided by 1 factorial, times x to the power 1. And then there's the rest of it. Well, you see, and the rest of it is, of course, something x squared plus something x cubed and so on. I won't worry about those in a moment. Well, 0 factorial by convention, 0 factorial and kind of like an empty product by convention has the value 1. And x to the power 0 would have the value 1 as well. Anything to the power 0 is 1. 1 factorial is 1 also. X to the power 1 is just x. And then, you see, everything else is either x squared, x cubed, x to the power 4, and so on. They're all those higher powers of x. Well, we can take a common factor of x out of all of those. Okay, so you could, and then it'd be something constant times x plus a constant times x squared, that higher powers of x. So this is what the Taylor series looks like, but you can see it's exactly what I had above. We have the linear approximation plus the error term. The error term does have that property that it consists of x times another function of x. The error term is x times that other bracket, which is x squared in it. That other bracket has the property that it converges to 0 as x converges to 0. Okay, because everything in it is at least x to the power 1. X or x squared, x cubed, etc. So this is like your epsilon. This here in the bracket is like your epsilon vectors. So what we did the other day by looking at this alternative form of the definition of the derivative, it is actually the first couple of terms of the Taylor series. And another way to provide more kind of motivation for the correctness of the formula is the following little argument. Suppose, so additionally, suppose a function f can be represented as a power series near the base point 0. Okay, we'll just consider the simplified version of the base point 0 for this. Suppose f could be represented as a power series. So not specifically a Maclaurin series, but just some kind of power series. Suppose we could represent our function f as a power series, and this is the general form for a power series, just an infinite polynomial in the variable x with various coefficients an, and we'll say that the an are all real numbers. Well, what we can do is we can show that if f can be represented like this, then the representation has to be exactly the Taylor series. So the Maclaurin series is really the only power series for representing functions. Okay? So we can show this has to be actually be the Maclaurin series. Maclaurin or Taylor series. So these two names associated to this kind of thing, Taylor series. And when you say Maclaurin series, I think you generally mean one for the function based at the base point 0. Well, the way to show this is just very neat, nice argument, is just to differentiate both sides. Okay. Now, there are some subtleties that do have to be justified carefully. Now, we're not going to spend the time on that here, but what we're going to do is we're going to, assuming we can differentiate infinite series term by term. So we've already proved that the differentiation operator is linear. So you can definitely differentiate the sum of two functions term by term. Differentiating the sum by differentiating each part and adding the two derivatives together. And by extension, that can be extended out to any finite sum. But you have to be a little bit careful about what you mean by differentiating an infinite series, and whether or not you're justified in differentiating that term by term. Okay? Going from the finite to the infinite isn't just a matter of expanding out the argument, because you never get to the end of an infinite sum. So there are some subtleties that you have to be careful about here. But just for the moment, we're going to assume that we can do it. So if we differentiate both sides, we get that the derivative of f of x is, well, let's just say d dx. So what does this power series look like? It looks like a0 plus a1 x plus a2 x squared plus a3 x cubed, etc. Now, if we differentiate that term by term, you see the derivative of a constant is 0. The derivative of a1x is a1. The derivative of a2 x squared is 2a2 x. The derivative of a3 x cubed is 3a3 x squared, so on. And evaluate at 0 implies that f prime of 0 on the left-hand side, well, when we evaluate the right-hand side at 0, of course, every term has an x in it, apart from the first. So every term will go to 0 when you substitute in x equals 0, and all you'll be left with is just the a1 on the right-hand side. So that's telling us that the coefficient of x in the power series has to be the first derivative of f evaluated at 0, as it is in the Maclaurin series. Differentiating again, gives that the second derivative of f at x, where we differentiate the right-hand side again, with respect to x, the a1 disappears, it's a constant. You get 2a2, and now we get 6a3 x and higher order terms. And evaluate at x equals 0, gives that the second derivative of f at 0 is indeed 2a2, i.e. a2 is the second derivative of f divided by 2, which it is exactly in the formula for the Maclaurin series. Okay. So we see agreement with the Maclaurin series. So in a sense, if the function does have a power series of the form we wrote down at the start, then it kind of has to be the power. It has to be the Maclaurin series. Okay. So that's some material on the Taylor series, or power series. Is there any question about that, or anything I could clarify on that for you? Okay. So second item we're going to look at now is some material on the notion of stationary points of a function. you may well have seen this before, but it's a nice application. It's one of the important uses of calculus, of the derivative, that we can apply to functions, and it's a way of solving optimization problems of various kinds. So we have this definition at the top of page 49, where a stationary point or a critical point, various terms used for it, for a function f of x is a point on the graph of the function where the tangent line has slope 0. So that means the tangent line is exactly flat, horizontal. Okay, the line with gradient 0 or slope 0 is the flat horizontal line. So these are characterized because, remember, the first derivative of the function gives you the slope of the tangent line. So wherever the first derivative of a function is equal to 0, wherever that happens, there we have a stationary or critical point of the function. That's what it's called. Now, for functions of a single variable, critical points exist for functions of any number of variables, but for a function of a single variable, which we're focusing on, these come in 3 types. There are local minimums, local maximums, and so-called inflection points. So these diagrams here illustrate what a typical local minimum and local maximum point would look like. So the point on the first graph is a point which has got lower value than any other nearby point. Okay, so locally, at least, it's a minimum for the function. It could be a so-called global minimum for the whole function if the function never went below that value. If the function never went below this value at all. Okay, we've only got a small portion of the function illustrated. And similarly, this point here for this function, that's a local maximum. Locally, at this point, the function has a value greater than any other nearby point. And you can appreciate, if you think of what the tangent line to the graph at both these points looks like, the tangent line would be completely flat. Okay. The other type of stationary point is a point of inflection. So this is kind of like a mixture of a local minimum and maximum. If you look to one side, it's kind of acting like a local maximum. So if you could only look to the left of that point, you would think this point was a local maximum. If you could only look to the right of it, though, you would think it were a local minimum. Okay, so it's smaller than the values to the right. Okay, but so this kind of behavior is called being an inflection point. Okay, if you think of what the tangent line to the graph at that point is, it's still a flat horizontal tangent line of gradient 0. So we are going to be interested in finding and classifying these points in various situations. So they're found by differentiating the function and finding the roots of the derivative, finding the points where the derivative is equal to 0. So you might do that, and then you have a bunch of stationary points, and then we'd like to be able to decide whether they're local minimums, maximums, or these points of inflection. And that can be checked using the second derivative. So if you look at the local minimum point, if you think of what the derivative is doing either side. See, to the left of the local minimum, we've got negative derivative, because the function is decreasing there. We've got negative slopes. 0 slope at the minimum point itself. And then to the right of the minimum, we've got positive values of the derivative, positive slopes. So the first derivative itself, the first derivative of this function is going from negative through a 0 value to positive values. So the first derivative is in fact increasing. As you move through the point from left to right, from in the increasing value of the x-axis, the conventional direction, as you move through the point, the first derivative is increasing. So a positive second derivative. The second derivative is the rate of change of the first derivative. If the first derivative is increasing, we'd expect the second derivative to be positive. A positive derivative of at a stationary point means you've got a local minimum. It's the opposite behavior for a local maximum, because you've got positive slopes to the left of the local maximum and negative slopes to the right, and zero slope at the maximum itself. So the first derivative is going from positive values through the zero value to negative values. So the first derivative is decreasing. So the second derivative, which is the rate of change of the first derivative, will be negative, because the first derivative is decreasing here. So a negative second derivative at a stationary point means we've got a local maximum. The other type of behavior, if the second derivative comes out as zero, means you've probably got a point of inflection. So if you think about the point of inflection, you've got positive decreasing slopes to the left and increasing positive slopes to the right. So you've kind of got the first derivative being positive, going through the value 0, and then being positive again. So it's like a local minimum of the first derivative. And if we were looking at the reflection, the mirror image of this behavior, which is also an inflection point, we would have a local maximum of the first derivative. Okay. So the way to classify the points is outlined there on that page, just a summary of what I've been saying. So negative second derivative for a local maximum, positive second derivative for a local minimum. Points of inflection kind of characterized by the first derivative having the same sign as on either side of the point of inflection. So in example 4.10, we've got a couple of examples there illustrating this method of finding and classifying stationary points. And I've got an example or two to work through here on the page as well. So let's just look at these initially. So in the first one, we've got this function x cubed minus x. So its derivative is going to be 3x squared minus 1. 3x squared minus 1. So when we set that equal to 0, we look for solutions to that. So you stick the 1 over the other side, so it'll be x squared equals a third. So that has two solutions, plus or minus the square root of a third. So that gives you two locations for stationary points of the function. To classify them then, we'd want to use the second derivative. So we obtain the second derivative of the function, so we differentiate the first derivative, so that would give us 6x minus 0, because the constant differentiates to 0. So the second derivative is 6x. So when you evaluate that at the positive square root of a third, you get something positive. 6 times the positive square root is going to be positive. When you evaluate it at the negative square root, it's going to be negative. Okay. So that means we've got a local minimum at the positive square root and a local maximum at the negative square root. Okay. Quickly just verify that that's correct by looking at the plots of the function. What was it? X cubed minus x. Yeah, and you see you do indeed have what look like two critical points here, a local minimum here at a positive value, approximately 1/2, and a local maximum at approximately negative 1/2. So that does agree with the notes there. Okay. There's another example there in part 2 as well, but I'll let you read through that. So I think I'll show you another example here on the page, which is a slightly more meaningful one, in that it's presented as an optimization problem. So where we're actually attaching some meaning to they were actually attaching some meaning to the minimum or maximum behavior of the function. This is an optimization problem. Okay, so you may have seen kind of problems like this before. They're kind of nice problems, and they illustrate the method well, but slightly more meaningful. So here we're talking about a box, which is a certain width there, a certain length, but we require the length to be 3 times the width. We have this requirement on the dimensions of it. It's going to have a certain height, h. Okay, so we need a box. We need a box of width w, height h, and length l, which is 3 times w. Yes, that's fixed. The box has to have these dimensions. We also require the box have a volume of 50 cubic meters. So that's another requirement. The box has to have a volume of 50 cubic meters. The material for the top and bottom, the box will have 6 faces. The material for the top of the box and the bottom of the box costs £10 per square meter. And material for the sides costs £6 per square meter. Okay, so we kind of think of it like the top and the bottom have to be fairly sturdy, and we can afford slightly cheaper material for the sides. Now, okay, of course, the way the world works is whenever there's a cost, you want to minimize the cost. Okay. So what are the dimensions of the box? It has to meet the requirements. The width has to be the length has to be 3 times the width, and it has to have a volume of 50 cubic meters. What are the dimensions of the box meeting the requirements? But with minimal cost. Okay, so given these requirements, it has to be 3 times long. Length has to be 3 times its width. Has to have a volume of 50 cubic meters. You've got these at £10 and £6 per square meter would be the main contribution to the material cost of the box. These other small ones, of course, the fixtures and fittings of the box, but material would be the main material cost. So how can we minimize the cost of this? Okay. Now, okay, so we need to start thinking about, okay, how can we represent these quantities using the various variables? Well, clearly the volume B of such a box is simply H times L times W. Volume of a cuboid box like this. Now, of course, we have the constraint that the length has to be 3 times W. So that means we can represent the volume as 3 times W squared H. But we have the requirement that the volume has to be 50 cubic meters. So actually the width and the height we started off using them as representing them with different variables as if they were independent quantities. Well, actually, we see that the volume constraint actually makes them be dependent on each other. And you could express that dependence as the height has to be 50 over 3 times w squared. So now let's think about, so that's the volume of the box. Now let's think about constructing the cost function. So the cost function is going to be, well, so look at the top and the bottom faces. So the top and the bottom faces have area L times W, and we've got 2 of them, and they cost £10 per square metre. So it's going to be 2 by 10 by LW. It's going to be 20 LW. Then the other faces, the material costs £6 per square metre. So we're going to have 6 times however many square metres. And there's 2 faces of dimension W times H, and 2 faces of dimension L times H. Okay. So two of the vertical sides have dimension W times H, area W times H, and the other 2 have size L times H. Now, this can clearly be multiplied out and simplified somewhat. And we also want to bring in this constraint that we've got using the h equal to 50 over 3w squared. So when you multiply this out, bring in the h equals 50 over 3w squared, your cost function is going to emerge as 60 w squared plus 800 over w. Okay. So what looked like at the start, when we first drew the picture of the box, it looks like 3 independent variables: a length, a width, and a height. But the requirement that the length be 3 times the width. Okay, so that reduces the number of variables to 2, the height and the width. But then the volume constraint reduced it further, because the volume constraint actually locks together the height and the width. They have to have, if you know the value of one, you know the value of the other one. So then the cost function also emerges as a function of a single variable as well. Okay, single variable. So if we want to minimize the cost, we can now use this idea of finding its stationary point, using the first derivative to find its stationary point. Yeah, I skipped over the algebra to get to the cost function, but it's just basic algebra of substituting 3 times w for L, and for h substituting 50 over 3 w squared. So now we seek to minimize, or now we seek the stationary points of cost. Stationary point or points of the cost function. So we'll call the cost function, this function, C of w, which is 60 w squared plus 800 over w. So we look at the first derivative of w. So the first derivative of w is going to be 120 times w, is what you get when you differentiate the 60 w squared, when you differentiate 800 over w, you get minus 800 over w squared. Now we want to find the zeros of this function. So given that we want to find the zeros of it, a convenient way to express it would be to put it over common denominator, w squared, and then we'd have 120 w cubed minus 800. Okay, so just bringing these two quantities together as a single fraction over w squared. Now we seek the zeros of w. So c prime w is equal to 0 exactly when 120 w cubed minus 800 is equal to 0. So when is a fraction equal to 0? A fraction is equal to 0 when the numerator is equal to 0, and the top of the fraction is equal to 0. So this implies that w cubed is 800 over 120, and we'll cancel a 40 out of both of those, I think. That'll be 20 over 3. So in fact, there's only one stationary point. Our one stationary point is the cube root of 20 over 3. Okay. So now we can find the second derivative. C double prime of 0, C prime of w, second derivative of the cost function. So that'll be 120. I'm differentiating this formula here. 120 plus 3 times 800 over w. No, sorry, plus 2 times 800 over w cubed. Okay, differentiating minus 1 over w squared, you get plus 2 over w cubed. Well, clearly, this second derivative is going to be greater than 0 at, well, at all values, really, of w. At all positive values of w, because it's, if you evaluate the second derivative at a positive value of w, it's 120 plus 2 times 800 over the positive value cubed. So it is going to be positive. So this minimal, or this stationary point value, the cube root of 20 over 3, is indeed a local minimum for the cost function. So if we take w cube root of 20 over 3, which is approximately 1.88 places, this will give you this. This gives the required minimal cost box. Okay, the length, which is 3 times w, will be approximately 5.65, and the height, which remember was 50 over 3 w squared, that would come out as approximately 4.74. Okay, but this picture of an original setup which seems to be multi-dimensional. So our original box depended on three variables. But with the introduction of constraints kind of reduce the dimensions of the problem. So here we had two constraints. We had this constraint relating to length and width. That obviously got rid of the length as an independent variable. But then the volume constraint fixes a definite relationship between the height and the width. So if you know one, you automatically know the other one. So bringing all those to bear on the original cost function. See, our original cost function was depending on three different variables. But when we imposed the constraints, we got the cost function out as a function of a single variable. And then seeking to optimize that in a minimal way to find the minimal value of that cost function, we could use the first derivative, we'll take the stationary point, confirm it was a minimum using the second derivative, and then find the optimal solution. Okay, so if you look at the end of chapter exercises, there's plenty of exercises on these to be working with. There's exercises 4.1 on page 48, just under the sample Maclaurin series. Then in the end of chapter exercises, questions 13, 14, 15, 16, 17, 18 are all the Maclaurin series. Then the optimization problems you'll have to, they're spread there. Questions 9 and 10. Question 22 on. Okay, so there's plenty of optimization problems there to be working with in tutorials. Okay, I'll see you all tomorrow again for another lecture tomorrow.